Welcome, Muhammad, to this new session. And in this session, we will start discussing the example regarding the buckling failure mode on columns for designing the cylinderness. And we'll have this example. This is a complete example. We'll clarify everything that we discussed regarding the concepts of the RC column cylinderness design. Okay, so we have this example. Raised column with effective length factor k is 1. So what we understand if we say the k is 1, what do you think?
If k is 1, you mean it's non-sway.
And it is pin, right?
Pin, yeah.
Okay, the height of the column is L is equal to 6 meter. Concrete compressive strength Fc prime is 28 megapascal. The steel yielding Fy is for grade 60 IC, so it is 420 megapascal. The unfactored load PD is 410 kilonewton. The unfactored live load also BL is 340 kilonewton. And the bending moment diagram for the column as shown in the figure. Now I will ask you again what is the MD and the ML and how we determine these values, or when or where we get these values, that column.
We get them from the resulting beam. These are the moments from the beam above, from the beam that this column is carrying.
The resulting negative moments, because normally it is negative moment in the ends, the beams that transfer to the column, right?
Yes.
Okay.
Yes.
And what D and L is refers to?
D is dead, L is live.
Perfect. So these are the surface loads, the surface moments, not the factored, not the ultimate. Okay, so these are unfactored, live and dead, respectively. Now, what's the questions? What we need to do here in this example?
We need to design a column, a square column that is enough to support those applied loads.
Okay, perfect. So we have these moments. This is the end moment bottom. This is the top moments. This is the story, maybe story 2, story 1, example. Okay, so first of all is compute the P ultimate. P ultimate, we have this combination 1 2 dead, 1 6 live. So this is the P ultimate, and also we have M ultimate 1 and M ultimate. Okay, the M ultimate 1 is 1.2 MD1 plus 1.6 ML1. Now what 1 and 2 refers to? 1 is refers to the bottom, 2 refers to the top, because the top are larger. As we discussed that in the formula of designing the buckling, we have M1 over M2 ratio, where M2 is larger. Is that right?
Yes, yes.
Perfect. So we see that M ultimate 2 is 78, while M ultimate 1 is 52. So this is the larger moment that we need to consider in buckling mode failure. P ultimate is like 1036, and from 1036 I think we discussed that a dimensions that preferable be used 1.4 by 1.4, not 1.4 by 1.4. I think
0.4 by 0.4.
Exactly, because 4 by 4 is 16, and 16, which means 1600, and it's near to this the ultimate, but it is larger, yes, and this help us to make the section negligible to resist the moment, the applied moment, because we discussed that we have an interaction diagram, which means how the cross section of a rectangle column, or even a square, or even circular, will react while we have both P ultimate and moment. And also maybe the column have biaxial moment, means M ultimate 1, M ultimate 2. 1 and 2 here refers to the two directions along the two dimensions A and B of the cross section. Okay. Is that clear, Muhammad?
Yes.
Okay.
Yes.
Now let's design the column as just for P ultimate, which means we just need to make the preliminary design. I mean the cross section, the area of steel, without considering the moment. Now we have this formula. Phi is 0.65, lambda is 0.8, 0.65 because it's a tie column, 0.8 for I think it's 50, and 0.85. FC prime is given. AG, we need to compute this AG, but AS as a minimum 0.01 AG, and M ultimate here is 0, as you see. From this equation, we have got the AG by millimeter square. If we now we have this AG, if we consider 27 by 27 centimeter, it will give us this AG, but we enlarge it like by 40 by 40 centimeters. Why? Because then we need to check this size that will have the capacity to resist the moment also. So we need to consider later the moment in our consideration, our computation. Is that clear, this point?
I see column size is 270 by 270, and then they're telling us try 400 by 400.
Yes, this is the first iteration, like to try 40 by 40 centimeters or 400 millimeters square section, because we need to consider the buckling, which means we have moment. This 27 by 27 will only resist the P ultimate, but we know that we have moment.
Yes.
Okay.
So when we did the calculation for the P ultimate, we got a cross section area that comes to this, which is 71.64. So okay, now I understand indeed. Go ahead.
Okay. So we need to check the cylinderness as we have this formula. M1 over M2 is given, right? And we have K, we have LU, the height, the unpressed length, assuming it's unpressed. Okay. So it is this way, and R is the radius of gyration. Now, R, we can compute it from previous sessions, equal to 0.3 h, where h is the side of buckling. And since it's square, means 0.4 by 0.4, in this point, or in this case,
cutting out.
Yeah, in this case, it does not matter. So 0.4 by 0.3 is 0.12, the radius of gyration. K is 1, LU is given.
Hello?
Yes, do you hear me?
Yeah, now I can hear you. Your voice was cutting out a little bit.
Okay, we have R, radius of gyration, is equal to 0.3 h, where h is the side of buckling. Since here we have a square section, so the side is the same, 0.4 by 0.4. So it's 0.3 by 0.4. R is 0.12. K is 1. LU is the height of the column. So since it is unpressed, so it's the full height. R, we have computed it. Then KLU over R is 50. Right? And if you think, or if you remember, we have formula to check if we can neglect the buckling effect, since KLU over R is less than or equal to 22. And in this case, no, it is more than 22. So we need to consider the buckling failure.
Oh, yes, I remember. Yeah.
Okay. So we have 50 now. So everything is given. Perfect. KLU over R. Now M1 is 52. We computed it in the bottom, and M2 is 78. Now M1 over M2, M1 over M2 will be a negative value. Means this sign plus, we need to make it minus. Why? Because M1 over M2, because the kind of deflection or kind of buckling of the column will be in single curvature. Why? Because we don't have a bracing in the middle. And I told you, we have bracing in the middle, then we will have a double curvature. Then we need to make it plus sign. Is that clear?
Yeah, so if it is a single curvature, it's negative.
Yes.
If it's a positive curvature, it's going to be...
yes,
okay.
I mean in the normal cases, we don't have bracing in the middle. Okay, so we need to make it minus. But if it is braced in the middle, the type of curvature will be double curvature, so make it plus. Now, just compute the formula, 34 plus 12 M1 by M2, and compare it with KLU of R, which is 50, and compare it also with 40. So it is 26. 26 is less than or equal to 50, right? And also, yeah, it is less than. It is less than or equal to 40, right? But it is not larger than 50. It is less than 50.
Yeah.
Hello?
Yeah, I can hear you.
Yeah, so it is I don't know what's in Arabic called mutabayina. So even if this okay, or even if this is okay, we need to check, or we need to consider the cylinderness. So since 26 is less than or equal to 50, so we need to consider the cylinderness. Is that clear at this point?
Yeah.
Okay. Now we need to compute the magnification factor for the moment. As we agreed together, we have two methodology for computing or designing the cylinderness for columns, where the first one would be to consider the second order analysis, okay, which means we need to consider that deflections. Then, or the second methodology is the magnification factor for the moment. Now, we have MC, where MC is equal to delta NS M2. Delta NS, we have this formula. B ultimate is given. BC is the Euler equation ultimate load. Cm is a factor, and I think is equal to 1. Right?
Yes.
Yes, we have all these formulas. So Cm, in normal cases, it is 1, but also we can compute it by this formula. So Cm is equal to, and you need to refer to the document I provided to check when Cm is equal to 1. But in this case, we'll check, or we will compute the Cm and use it in our formulas. Okay?
Yeah.
Okay, Cm is equal to 0.6 plus or minus 2.4 M1 over M2. M1 over M2 is given, so it is 0.86. P ultimate is given, or is computed. K since it's equal to 1 because it's pen normally. LU in millimeter, be converted in millimeter. EC, the concrete, regarding the FC prime, so it is 28. So EC is equal to 2480. 870. IG, because we have a square section, then it will be equal to which is the moment of inertia. So it's equal to, so it's a geometry a geometry factor. So it's equal to 1 over 12 by the side power 4. Okay, and in millimeters, unit will be millimeter to power 4. Now we have to compute also beta DNS. because okay, so we will need it for the other computations. Now, beta DNS is equal to 1.2 B dead over the B dead plus B live. So B dead is given, B live is given, B ultimate also is given. Then beta DNS is given or is computed 0.475. Now EI is given and E is computed. So we can compute EI. All your equation, PC, it's depend on EI, pi square over KLU is computed. And EI is the effective, where it depends on IG. So it is not the IG by EC is equal to 0.4 ICIG ECIG over 1 plus beta DNS. Beta DNS is computed from the ultimate dead and live formula. Okay, EC is computed, IG is computed, then I can compute the EI, the stiffness factor effective. Once it's computed, I can compute the BC, which is the Euler ultimate load. Then BC, B ultimate is computed or given. TM is computed also. I can compute the delta NS, which is factor to magnify to make the magnification for the moment, for the large moment. We agreed. So I can compute then MC, the magnified moment. Do you have any questions on this procedure?
No, so far it's very clear. I can understand it.
Okay, I hope. So you don't have any questions, I think we can continue.
Yeah.
Now, as a summary, we have computed the MC. Okay. Since we computed the MC, now we need, if you think and if you remember, we need to compare this MC by the minimum moment we need to consider, which is related to the minimum is eccentricity. Is that right?
Yeah. If I remember, MC should be more than a minimum, right? I don't know. Maybe I remember it correctly.
Yes. We can refer to the document again. Okay. It's okay. We can refer to the document and check that. If M minimum exceeds the M2, then we need to take M is equal to 1. Okay? And M2 must be greater than M minimum. Now M2 is computed. Now we need to compute M minimum. If M2 is less than or equal M minimum, M2 in all cases must be greater than M minimum. Okay?
Yep.
Which means M minimum should be less than or equal to M2. Is that clear? M minimum should be less than or equal to M2. Okay. Now referring back to the example. Okay. We computed the MC. Now we computed the M minimum. The ultimate is given. Minimum eccentricity would be 15 centimeters plus 0.03 H. Okay. H is given 0.4. E minimum 0.027. Then I can compute the P ultimate by E minimum to check the M minimum equal to 28. Now compare it to the M ultimate. Is that less than or equal to 78? Right.
Yeah.
So it's okay.
M2 is greater, yeah.
Okay. We can continue now. Now MC is equal to the delta NS we computed 1.33 by the M ultimate. So we have this make the now. The column dimensions are 400 millimeters square, right? So imagine we have this section and it's B. We have B and H, B for the width, H for the length, not the height, as a plan to imagine a cross section. We have B ultimate is computed and M ultimate, where M ultimate here magnified moment. You see the MC.
Magnified and ultimate.
Yes, because we need to consider the buckling. So concrete cover here also would be 60 in the example. Okay, no worries. Now we need to compute a factor called gamma, where gamma is equal to. Now, before we compute these things, I need to refer to the interaction diagram so that you understand these steps, because we just need to compute like a coordination and to plot this coordination as xy in terms of P ultimate, M ultimate on the interaction diagram that is related to the column. And if this point is under the curve or under some regions, so this means the section can resist the buckling under this moment, under this P ultimate. Is that clear?
Yeah.
Okay, perfect. So let's refer to this interaction diagram. So we have this interaction diagram. As you see in the interaction diagram, we have here FC prime, where each interaction diagram have the FC prime. Now, to convert the KSI to megapascal, simply multiply by 7. So 4 by 7 is 28 megapascal, and it's our case, right?
Yeah.
The same way as for if yielding it. Also, it's 60 KSI, so it's like 420. Gamma here is 0.9. We have for each interdiagram gamma. Now, what's gamma? Let's zoom in. We have this section. You see it? So this section, the end of the concrete edge, in this section, we have this term H. Now, gamma H is from center to center, the rebars, the corner rebar distance. Now, gamma is equal to this distance from center to center, corner rebars, by the total H. So gamma H, the distance, over the H, I get the gamma. And gamma in here should be 0.9. Clear?
Okay.
Is that clear,
Yep.
Muhammad?
Yes.
Okay.
Yes.
So in the x-axis, what do you see? What we have in the x-axis?
In the x-axis, I see. What is that? Phi?
Yes. Go ahead. Phi mn.
You
see?
Yeah, the BH squared.
Okay. NKSI. So we have phi mn over ph squared. In the y-axis, we have phi bn over ph. Also, it is KSI. Now, we have these curves.
So this, okay, one is for the axial, one is for the moment, right?
Yes, this is for the ultimate, the axial load, and for the moment. We need to compute these factors, because these interactions are derived from these factors. Depends on p h squared. So again, it is a matter of moment of inertia along the h and along with the b axis.
Okay.
Now we have also other ratios or other factors. Rho g. Okay, in this case it is 0.01, and we have up to 0.05. And we have another factor, which is E over H. E is the eccentricity, and H is given by the side of the. Now, I think everything is clear at this point.
Yes. EIH or ELH?
EH square, where?
Let's go to the graph, yes.
E over H.
E over H, or is it? Okay. I thought it was EIH.
No, it's E over H. E over H.
E over H, yeah.
And you know the extent.
So that height,
what I mean by the extent. This is the center, the toroidal point. This is if this B ultimate, so we have eccentricity from the center. Okay. Now simply gamma is equal to what? If we need to compute it, is equal to gamma H if we know the center to center distance, but we didn't yet find the design, right? So we need to make compute it. So gamma is equal to H minus 2 covers to the bars to the centroid, center cover, not the clear cover to center. We have 2 covers from these right and left sides over H, over the side wall distance. Now, then we need to determine phi Bn over Bh and phi Mn over Bh squared. Since we determine these values, we can plot the point on the graph and see if the point lies under the curve or out the curve. Do you have any questions at this point, Muhammad? Is that clear, Muhammad?
Yes.
Okay. So we need to finish the example. Now we have the cover, complete cover, large but okay. Gamma is equal to the side where it's 40 centimeters minus 2 by 6 centimeters, 60 millimeters over the edge for 100 millimeters. Then gamma is equal to 0.7. And I told you for each interaction diagram we have gamma. That right from this concept. Now it's okay. We can compute or we can plot the point, the coordinations in these factors in the graph of 0.7 gamma. But if we didn't find in the internet or in this document an interaction diagram that based on gamma equal to 0.7, simply we can make interpolation between, for example, 0.9 and 0.4, for example. Okay?
Okay.
Phi Bn, we have the phi Bn, the ultimate, phi already computed. Because we make the combinations. So simply the B ultimate by 1000, just to convert it from kilonewton to KSI, we need to multiply it by 1000. Okay, over BH, P by H, the same. The distances, the sides of this section, by 7 in the here. Why 7? Because we told you that convert from kilonewton to KSI, we need to multiply, convert from megapascal to KSI. Yeah, we need to.
From megapascal to KSI.
Yes, exactly. The idea that we have a factor of 7. So we need just to compute it in Newton and then make it in divided here by 7. So simply multiply by 1000 over 7, so we get in KSI. And also for phi Mn, M ultimate here, M ultimate which is MC, the magnified moment, phi. Here, moment it is in Newton, it is kilonewton meter. We need to convert kilonewton to Newton by 1000 and another 1000 for meter to millimeter, and also by 7. And we get these values. I mean, we get the point on the graph, right?
Yeah.
Okay. So we have
that's all we need.
Yes, we have the row 0.01. So 0.01 by 400 by 400, and you remember that this dimensions or this section size is like a trial and error, right? Because without considering the moment 27 by 20. So we tried that to see if side 4 meters square section is okay for a moment. So we need to compute area of steel for this case, and we need to take the row to be equal to 0.01 since the interaction diagram is depending on. Okay, now we have this section. Simply, we have 40 centimeters by 40 centimeters, and these reinforcements already given, suggested by this area of steel suggests we have 8 by 16 and a stirrup of by 10 over 25 centimeter spacing. So now this is the ties reinforcement. We will talk about it later, design of shear core column, but we need just to focus in this session on buckling design. So finally, compute the MC. In summary, we compute the MC. We make the check. We need to make the check if the column is okay or can take the resistance or have the capacity for the moment in existing of axial load also. So we need to take this point, which is 0.93 in the y-axis, or let's say 0.23 in the x-axis, 0.93 in the y-axis, with gamma is equal to 0.7 and rho is equal to 0.01, the interaction diagram, and check that point. So let's go. Let's back to the interaction diagram. So before we go, you need just to memorize these numbers, 0.93, 0.23.
Alright, 0.93, 0.23. Okay.
Okay. We have 0.6 gamma and we have 0.75 gamma. We don't have 0.7. So simply we need to take an interpolation. So assuming now I will not make an interpolation because it's very simple, but I will focus on the concept. Assuming it's 0.75. So we have 0.23 and 0.93, right?
Yeah.
Okay, 0.23.
0.3.
So the graduations here
1, 2, 3,
is 0.8 to 0.9, 0.9 to 1. So each square here is like 0.01, 2, or we have 1, 2, 3, 4. This is from 0.01 to 0.2. We have 0.1.
5.
Yes, it's like 0.02. 0.02, 0.04, 0.06.
Every square is 0.02.
Yeah, it's 0.02.
Yeah, every square is 0.02.
Okay.
So it's the third square from 0.2.
Okay, so it's like here in the first square.
Half, yeah.
0.023, 0.022 or 0.0. Does not matter. Now we need other point, which is 0.93, right? So it will be here 0.058. So in the top of the last square for the one. So here we have this point right here. And this point, yeah, this point here is under the scale for rho is equal to 0.01. So in this case, the column can resist the moment and it's safe for designing or to considering a 0.4 by 0.4 of height 6 meter column under that P ultimate which equal to 1036 and M ultimate magnified moment is equal 105 kilonewton. I hope everything is clear, Muhammad.
Yes.
Yes. Do you have any questions?
Yes. No. It's very clear.
So I hope you understand this session. We discussed the interaction diagrams, discussed the buckling failure with a practical example, and you understand all your DC, the term PM, M ultimate, 2, what 2 refers to, what 1 refers to, DC limitations checks, and everything. I hope everything is clear for you, and the procedures.
Very, very clear. I will try to do an example.
Okay.
Then before next class, I'll show it to you.
Yes. And in the next session, inshallah, we will discuss maybe the same example or like semi-example in ETABS for sure to make the comparison, because you know we stopped on ETABS on overstress problem, right?
Yes.
Yes, we see that overstress problem, and once we right click after we make the design by ETABS, we see that we have issue of delta NS exceeds maximum allowed, right?
Yes.
And from previous lessons, we discussed that delta NS have a maximum allowed, and it is if it is reached the maximum allowed value, and I think it's 1.4 something. Yes, if no as a value delta NS exceeds the 1.4, then we need to enlarge the section. Means the section is very thin regarding the height, regarding the moment, regarding the ultimate, regarding the moment inertia, regarding the stiffness. All of these factors are playing together.
Okay.
And do you see the ETABS? I'm sharing the ETABS now.
Yeah, I can see it.
Okay. So I will just zoom here. You see, exceeds 1.4. The same issue that we discussed just in a while. The delta NS should be not exceed 1.4. This refers to ACI. So the document I provided you is just right from the ACI concepts, from the ACI formulas. So it's really helpful. It's also from Dr. Ibrahim Erman from Najah National University. So many thanks for him because he provided this helpful information, helpful guide for structural engineers, civil engineers. And I hope everything is clear for now, Muhammad. If you have any questions, feel free to ask me. And yes, I hope you enjoyed this session and you understand well the buckling failure, the design, the procedures.
Yes, 100%. I understood clearly.
Okay, so I hope so. So if you don't have any questions, I think we can stop this session and see you tomorrow, maybe inshallah.
Inshallah, inshallah.